Hello, everyone. My name is Bruce Baer, Dean of the University of Washington College of Forest Resources. And on behalf of the entire college, I wish to welcome all of you to this three-part lecture series entitled Sustaining Our Northwest World, Tales from the Forest. Our intent in this series is to highlight the dynamic balance required to meet the growing natural resource needs of society while sustaining the environmental, economic, and cultural values we associate with our region's urban and wildland resources. This lecture series is a companion to the college's Denman Forestry Issues series, also seen here on UWTV, and both series contribute to the college's vision of world-class leadership in sustaining natural resources and environmental services throughout the region and beyond in order to improve the lives of future generations while satisfying the needs of people today. Using objective science to address our complex and contentious natural resource issues is a necessary, but by no means a sufficient condition for finding balanced solutions. We must also properly recognize and incorporate economic, social, and cultural values into the policy formation and decision-making processes. In essence, all three values, environmental, economic, and social-cultural, must be considered to achieve a balanced, sustainable solution that ensures the proper stewardship of our natural resources. We are pleased to present this lecture series in partnership with the University of Washington Alumni Association. We are also grateful for the support of the Rachel A. Woods Endowment, which is underwriting a portion of this series, and to members of the college's Dean's Club for their financial support. I encourage each of you to contact the college at www.cfr.washington.edu to explore the broad nature of natural resource issues that we are studying and to learn how our college plans to educate the next generation of natural resource scientists and leaders while creating and leveraging new technology to sustain our Northwest world. Our lecture today will be presented by the University of Washington College of Forest Resources Professor Linda Brubaker, who will discuss responses of forest vegetation to climate change over long expanses of space and long periods of time. Her research uses the science of dendrochronology, which is the dating and study of annual rings in trees, to investigate the response of forest vegetation to changes in the climate. Professor Brubaker has used this approach to investigate the history of insect outbreaks and climate variations in the Pacific Northwest based on analyses of ring width patterns in major conifer species. She has also conducted research on long-term vegetation responses to climate change centered in the late Quaternary, which is about the last 2.5 million years, history of Alaskan ecosystems. In these studies, she uses the science of paleontology, which is the quantitative analysis of pollen, spores, and related microfossils in sediments that are revealed in cores she has taken from lake beds and wetlands in Alaska. Her lecture is especially important in light of the ongoing discussion of the probable impacts of global climate change and its effects on the forest of the Pacific Northwest. Suffice it to say that these probable impacts might seriously affect the sustainability of our forest as we know them today. Now, to discuss this issue related to climate change and its effects on forest ecosystems, I wish to introduce Professor Linda Brubaker, who will speak on the topic, A Warmer Pacific Northwest, Lessons from the Past.
For the past several years, the question of whether the Earth's atmosphere is warming has received a great deal of attention. And as a result, the general public is not really surprised when you see headlines such as this one that appeared in the Seattle Times just last October. Although I don't think that anybody knows the truth about global warming, it certainly is clear that the topic of global change and global warming has become very much debated, even at national and international levels. And in some cases, it has even been used to set policy at those levels. Well, when anything is as big as it affects the whole globe, I think it's natural to say, well, what about my backyard? What is it doing? What might be happening here? So tonight, I would like to discuss some of the potential consequences of climatic warming in areas that we're familiar with, especially the western side of the Cascade Mountains at mid to high elevation, where forests exist that look something like this before the days of logging. This is an old-growth forest that's probably 400 to 600 years old. And the climate in this region is moist and is cool. Even though there is a short dry season in the summertime, there really are infrequent fires. Hundreds of years might pass between fire events in the Pacific Northwest. And partially as a result, the trees can reach very large sizes and reach many centuries of age. And these forests are really renowned for their biomass accumulation, the very irregular structure of the stand. And this stand, you're looking from the Canopy Crane near Wind River, and so you can see the variation in tree heights and forms over these very old stands. But instead of talking about this time now, where we're familiar with the forest, I would like us to focus on a time in the long past. This is the period between 11,000 and 7,000 years ago. It's called the early Holocene. The Holocene is a geologic period, which is the present interglacial when the Earth's ice caps are very small. And the early Holocene was the warmest and driest portion of the present interglacial. Well, I think there's several reasons that we might learn something by looking at the past. When we're thinking about the future, we can look to the past because it can provide some maybe glimpses of what the consequence of climate change. The Earth's climate is always changing at different time scales. And if we can go to the past and find an interval when the climate is warmer than present, but it would still have the same suite of species, maybe we could take that snapshot as some idea about what the future might hold. Another reason to look to the past is that when we do this and we look at different time frames and different locations, many times we see repeated themes. Information about the general nature of forest responses to climate change. And those, I think, that second reason, I think, is actually more important than the first. And that's because there are some cautions in looking at the past and thinking they will match the future. And that caution is mainly because the things that cause climate to change will vary over time. And so the causes of the major forcings of climate during the early Holocene are really not the same things that we think are going to control climate change in the near future. So we can't use the past as an exact roadmap into the future, but I think we can get some important lessons about the nature of responses to climate change. So the climate forcings are fairly well known. One of the very important controls over climate variation is the amount of insolation or solar radiation coming to the Earth's surface at different latitudes and different seasons. Sea surface temperatures play an important role, as do ice volumes. And then, of course, greenhouse gases, which are the forcings that we're most concerned about in the near future. Well, the early Holocene stands out in the geologic record as a period of insolation extremes. At our latitude, there was about 10% more radiation in the summertime and 10% less radiation in the wintertime. Now, we know this largely because of the work of a single person, Milutin Milankovitch, who worked in the first part of the 20th century. And part of this time, he did his work in prison. I think he decided you shouldn't waste your time no matter where you are. And he took advantage of this and started making calculations of variations in the amount of solar radiation that hit the Earth's surface at different latitudes and different seasons. And he did this over hundreds of thousands of years. And it was known that there's variations in the amount of solar radiation due to changes in the Earth's orbit as it goes around the sun. There are many things that change in the Earth's orbit. One is the shape. Sometimes it's round and sometimes it's elliptical. The tilt of the Earth's axis changes. Sometimes it's more extreme than at other times. And then also the location of the Earth on the orbit at different seasons will change. This diagram depicts the current conditions where the northern hemisphere, in the northern hemisphere winter, we're actually, that's when the Earth is closest to the sun. It's winter because the tilt is away from the sun, so the radiation comes in at more oblique angles. But we're actually closest to the sun in the wintertime. It's January 11th, just about a month ago. So this means that the seasonal variation is not as extreme as if we were, say, far away from the sun during the winter. And as it turns out, during the early Holocene, the configuration of the Earth relative to the sun was quite different. During the early Holocene, the Earth was closest to the sun in the summer, and also at that time, the tilt of the Earth's axis was more extreme. These two things together made this period a time with higher radiation in the summer than we have now, and less radiation in the winter, which means the summers were warmer than they are now, and the winters are cooler than they are now. Now, his work was acknowledged but not accepted as a theory of climate change until work was done on deep sea cores. And these cores were taken in the North Atlantic initially, and oxygen isotopes were examined, and they give some record of the amount of water that's actually incorporated into the ice sheets. So these oscillations of the oxygen isotope over long periods of time, this shows 800,000 years, were very similar to the plots of solar radiation that were predicted by Milankovich's theory. And so as a result, when these two records and explanations came together, there was acceptance of Milankovich's theory as the likely best explanation for these long-term climate changes. I've circled the peaks which indicate the interglacials, and these are the peaks are the four warmest interglacials over this period of the record. And I point them out to indicate that the present time that we're in, the Holocene, is one of the more unusual periods of time over this very long record, and it's one of the warmest interglacial periods. So the question is, what were the Pacific Northwest forests like during the warm early Holocene? And I'll use two main examples, one from the Olympic Mountains and the other one from the Puget Lowlands. But I think it's important to know a little bit about the source of the information. How do we know? And actually, if you want to know about past forests, you go to lakes. And the information contained in the sediment of those lakes tells you something about the history of the forest. When I looked at this picture the other day, was taken 2 summers ago in some field work in the North Cascades, and I looked at it and said, that's why I got into my field. It was something like this, and it looks quite enjoyable, but actually, you know, it's quite a bit of work. You put pipes down through a casing into the sediment, and there's a hollow tube at the bottom of these pipes, and they gather the sediment, and you bring it up to the top of the raft and push it out, and then you can see the core of sediment. And if you scrape off, this is the fun part, you scrape off the outer mud, and you can see what's inside the core. And you can often visually see quite a bit of variation that'll tell you something about the environmental history. This picture is of a fire in Alaska taken a couple of years ago, and the core at the bottom is a sort of a slice exposing the inner part of the core, and you can see light and dark alternating bands, and the dark bands are the charcoal. So with fine records like this, we can reconstruct something of the fire history of a region. Volcanic eruptions leave distinctive layers in the sediment. This graphic is an artist's idea of the eruption of Mount Mazama. Mount Mazama currently is called Crater Lake, and when it erupted 6,800 years ago, the volcanic tephra was carried long distances, and virtually all wetlands and all lakes and all bogs in the Pacific Northwest have this distinctive orange band, which comes from the material ejected from Mount Mazama, leaving Crater Lake. Floods are also recorded in sediments as erosional events. This is a picture taken in the Dalles, and these people are standing on the upper balcony of a hotel. It's called the Great Flood of 1894, and it happened in June. There was a flood at the same time, the Fraser River. Seattle didn't flood, so the source of the water was probably from the interior part of the western part of North America, but it flooded way above the terraces on either side of the Columbia River, depositing this distinctive layer of silt in deposits in that area. When you look at the sediment under the microscope, you can see the individual particles of charcoal. You can see the clastics, which are the inorganic material. Tephra often will have a distinctive shape and definitely a distinctive mineralogy, and then the sand and the silt particles can be seen very clearly. But the record of the biology of the past vegetation comes from pollen grains that are well preserved in lake sediments. And these are really interesting objects. Can be very ornate. There's a great diversity in their shape and in their wall design and ornamentation. This slide has several pictures of insect-pollinated pollen types. The upper left is a pollen grain of ragweed, and you can see the spines that stick out on either side. I often think about those as mechanisms that will let the pollen grain become entangled in the insect hairs on the bodies and be efficiently carried from one plant to another. And the other pollen grains have very elaborate walls with crevices and creases and knobs and holes, and I think those are probably also aid in the dispersal by insects. Now another whole set of plants have pollen that's dispersed by the wind. And these will have some features to the pollen grains that make them more buoyant. In this case, this is a pine pollen grain, and you can see the big air sacs on either side, and that makes the grain buoyant. And these pollen types are carried long distances in the wind. And then finally, if we're really lucky, we can see leaves and seeds. These two leaves came from samples that were over 6,000 years old in the Olympic Peninsula. And leaves and seeds are very helpful because they give you precise or reliable information that a plant was growing very close to the lake, because they're not blown long distances the way the pollen can be. And also the leaves and the seeds often can be identified to species level when sometimes the pollen can't. So Yahoo Lake is the site on the Olympic Peninsula. Now this lake was named a long time ago, long before the .com time. So I don't know the origin of this lake, but I'm sure there's a lake name, but I'm sure there's a very interesting story behind it. The lake is currently surrounded by an old-growth forest dominated by western hemlock, western red cedar, with some Pacific silver fir. And as you can see from the picture on the right, it has a classical old-growth heterogeneous structure with many standing snags and gaps in the canopy. And the the foliage extends from virtually the ground level to the top of the canopy because the stand is so old and it's lost so many of its original members that the light can penetrate deep into the stand. So this is an example of old growth forest type that was very extensive in the Pacific Northwest before logging became extensive. The Yahoo pollen diagram tells you many things about the history of this location. Now, pollen diagrams are typically shown like this. The horizontal blue bars represent a particular sample, and the length of the bar represents the percent of the pollen type in that sample. The vertical axis is time. We can date the sediments by radiocarbon techniques. So at the bottom of this record, it starts at 13,000 years ago and goes upward to the present, the zero being the present. And I've plotted the species of trees that tend to indicate moist conditions: mountain hemlock, silver fir, western hemlock, western red cedar. And you can see that the overall impression here is that the trees that indicate moisture are present early in the record, and then there's a period when they are rare, and then again about 7,000 years ago, they become more abundant. So this early Holocene period from 11 to 7,000 years ago is characterized by a reduction in species that require moist climates or moist sites. And during the early Holocene, there is an abundance of pollen from species that indicate the existence of major disturbances to the site and also some indication of disease. Douglas fir and red alder require some major disturbance which will allow sunlight to hit the ground level, and also they require exposed mineral soil for seedling germination. So Douglas fir and red alder indicate that the areas around Yahoo Lake were disturbed fairly frequently. Douglas fir has very thick bark, and so it's well adapted to fire. So it's very likely, just from the inferences from the trees, that fires were frequent during this period of time. Now, mistletoe is a parasite on the crowns of trees. And the two host species potentially for mistletoe would be western hemlock and Douglas fir. The mistletoe cannot be identified to species, but I think that because of the similarity of the mistletoe pollen record to the Douglas fir, that this might actually be the parasite on Douglas fir. And this would be interesting because presently Douglas fir mistletoe only occurs east of the Cascade Crest, where the climate is warmer and drier, and the trees are likely more stressed and more susceptible to disease or a parasite like mistletoe. So this would be an indicator of a potentially stressful and most likely dry climate. Now, when we add the charcoal record to this sequence, we can see that there's been a great change in the input of charcoal over time. And earlier in the record, there are distinct charcoal peaks, many charcoal peaks, and a great deal of charcoal overall. And as the time progresses towards more recent times, the amount of charcoal decreases, and there are many fewer peaks. So the early Holocene, this warm period, was characterized by a time of, I think, frequent fires that allowed Douglas fir and red alder to become established. Red alder may have also been favored by more flooding during this period of time. And then a less abundance of the trees that require moist conditions. So when I think about these records, I think it's interesting to put them in a larger context of the Olympic Peninsula as a whole. So let's step back and look at the potential changes in the major forest zones on the Olympic Peninsula. This diagram indicates the major forest zones. The zones are named for the species that will be most common in those forests after long periods of time without disturbance. There are several species in each zone, but there's only one name given to it for that species that will be there over the very long term. Now, when people discuss what the potential consequences of climate warming might be, I think they and especially in mountainous areas, they think, well, the forest will just move. If it gets warm, they'll just move up higher in the Cascades or the Olympic Mountains, because as you go higher in elevation, the temperatures decrease and the moisture levels increase. So many sort of, especially early models of sort of thinking about future climate change, simply moved the intact vegetation zones up in elevation. And they might be worried about the alpine, because if the mountains are too short, there won't be places for the alpine species. But generally, it's a simple idea that species or forest zones are just going to move to some new location. Well, when we put all of our records together from the early Holocene, we see a very different picture. Certainly, there's areas along the Pacific coast where Sitka spruce dominated throughout the entire record, including the early Holocene, and subalpine fir in the high elevation eastern areas was dominant in those forests. So they actually had very little change over the past 12,000 years. However, everything else in between was significantly different during the early Holocene. And I think especially striking is the absence of these forests that are characterized by moist species. Mountain hemlock, silver fir, western red cedar, and western hemlock were extremely rare during the early Holocene. And at most sites, they're really below the detectable level by pollen analysis or the analysis of leaves in the sediment. In contrast, Douglas fir was very abundant. Now Douglas fir is fairly rare at mid-elevation on the west side of the Cascades, but its populations were very high at that time, as well as on the east side of the Olympics, I mean. So these forests were fundamentally different from the forest zones that we have today, and the response to this warming was not a displacement of existing forest types. It was a fundamental reorganization of the forest types, because the species themselves responded differently from one another to climate change. And apparently each species has a unique relationship to climate, and when it changes in a complex way, they behave according to their own relationships. And you might have coming and going of species that currently occur together, but at some other conditions they might not occur together. And I think it's worth sort of asking about how climate change affected human populations at the time. The early Holocene is characterized by a period called the lithic phase, and most of the evidence of the economy during this time comes from stones. Lithic means stone. There was evidence of hunting of big game like elk and deer because of these spear points. The choppers are sort of generalist tools that are held in the hand, used for a variety of tasks. So it appears that the human economy during this period of time was strongly oriented towards terrestrial resources. And then when the climate became more moist and cool in the later Holocene, there was a shift in the resource base to a more marine orientation. And at this time, in the late Holocene, you see the first evidence of shell middens and fish hooks and various objects like that, which indicate a very strong change towards marine resource base. In addition, you see evidence of the wide use of western red cedar. Now, western red cedar is really a remarkable tree, and it can be used in so many different ways. The foliage has medicinal qualities. The bark is really thin, and in the spring, when the cells are dividing underneath the bark can be dislodged at the base and pulled just very easily off of the underlying wood. And the bark itself is very pliable, and it is waterproof when woven into baskets and clothing items. In addition, the wood is lightweight. It's easily worked with simple tools. The grain is straight, and so it can be easily split, and it's very durable and will last a very long time. So western red cedar became a very important component of the resource use of people during the late Holocene. And this change from economic base of the cultures certainly is related to the shift in climate from the early Holocene to the late Holocene. So I think the take-home messages from the Olympic Peninsula are fairly straightforward. Climate change from between the early and the late Holocene caused shifts in forest composition, not just displacement, but intact, but the actual composition species that were growing together in any one place. Fire regimes were affected, tree pathogens responded to climate change, and then certainly the human economy also responded to climate change. So let's shift now to the Puget Lowlands during the early Holocene. This site is at Markworth State Forest, which is about 30 or 40 miles to the east of us. The Puget Lowland was dominated by very old forests prior to logging. The picture on the left probably resembles Markworth Forest before logging. The picture on the right comes from Markworth Forest, and you can see the remnants of the very old large Douglas fir tree in the center. And the trees that have come up came in following logging. Now, the area was railroad logged, and the extension of railroads into the forest made the extraction of the wood very efficient, but I can't say that it was a safe thing to do. If you look at this picture, you can see an accident along the way, and so it certainly was effective, but I can't say that I would want to have that as my profession. Another thing you might look at is the complete disregard that logging had for paleoecologists that might follow, because there are logs strewn all over the place. And I want to draw your attention to this person who blew up here because of his stance. And this is like, I think, the position you take when things are not going well. It was sort of back on one foot and hands on your hips or in your pockets. And then this reminded me of the stance of Ethan Cuddebeck, who was an important part of our research team as an undergraduate for several years. And he's standing on some logs, which I think came onto this site from railroad logging time. And the site is a tiny wetland which accumulates sediment over time and keeps a record of the vegetation around that site. And we were not happy at this time because many of the sites were disturbed by the logging operation itself. And so we had to take probes and mini cores to find some that were not disturbed. This record also shows several plants growing on the wetland surface that can provide some indication about the conditions of the stand and the light at that location. These shade indicators are devil's club, sword fern, skunk cabbage. But when you see pollen or spores from these in sediments, you know that the site was surrounded by a fairly dense forest that cast a great deal of shade on the site, because these species do not grow in sunny areas. Now, the pollen record from this site has some similarity to the pollen records from the Olympic Mountains. This site also starts about 13,000 years ago. At the base of the record, between 13,000 and 11,000, there's indicators of moist conditions. And then again at around 7,000 years ago, there's an increase in moist species that indicate moisture. And then in between, in the early Holocene, these moisture indicators are quite rare. And like at Yahoo Lake, you also see evidence of Douglas fir being common during the early Holocene, and alder. So that again would give you some suggestion that disturbances were common during the early Holocene. A new component of these records are some of the shrubby or herbaceous species that indicate sunny environments. I've listed 3 here: cattail, hardtack, bracken fern. And those, the pollen and spores from those taxa are 5 to 10 times the number of pollen from the other tree species. So we know at this time the forest was not dense and did not provide shade over the site. Instead, it must have been an open area because cattail and hardhack and bracken fern will not grow in shady environments. And it's very likely that fires were an element that kept these, the landscape fairly open. But the charcoal record does not have abundant charcoal in the early Holocene, and I think this is possibly because the fires were low-intensity fires and did not produce very much charcoal. But about 8,000 years ago, there was an increase in the amount of charcoal, many very distinct peaks, and this increase in charcoal and evidence of fire coincides with the establishment of trees. So at the end of the early Holocene, when it was still fairly dry, but forests were beginning to develop, there were probably a series of fires that caused reestablishment of those stands. And it wasn't until about 4,000 years ago that the current fire regime of very infrequent fires was established at this site. So the early Holocene is characterized by a period with increasing fires at the end of it and the strong evidence of an open canopy and possibly the absence of forest near the site. These are the indicators of sun, and you can all imagine where you would see cattail and hardhack. And hardhack, the scientific name of the genus is Spirea, which I think is a much nicer name than hardhack, and one that you might recognize as a plant that you might see in nurseries, and they really require a great deal of sun. Okay, so when I think about the Puget Lowland, instead of the old-growth, continuous, dense forest that we're familiar with in that area, I really think of an open landscape, and a landscape that might have large areas without any forests at all, or maybe scattered trees. Very different from the forest that we have currently in the Puget Lowland. And actually, there may be a few remnants or a few legacies of this forest that are located south of Olympia in areas that now are mainly in Thurston County and Pierce County. If you see the blue in the map of Thurston County, that's a low elevation area, fairly flat. And that's the area that received meltwater as the Puget Sound lobe of the last glaciation was melting. There was a lot of rapid water that deposited very coarse soils in those areas. And those areas continued to be very dry because of their soils, not so much because of the climate. And you've probably passed through many of the remnant prairies, I think, from the early Holocene. Just going between Seattle and Portland, you might have looked to either side of the road and seen open areas that might have been pastures or abandoned fields or something like that. But if you're paying attention during April, you might see a sort of a floating carpet that you see in these areas of blue. This is the flowers of camas. Camas is in the hyacinth family, and it has a large bulb, which was a very important food source of the Native Americans. And they managed these areas and probably used fires to keep them open. But presently, they are being invaded by Scotch broom and are of great conservation concern because of many of the species in animals and plant species are becoming very rare and potentially endangered. And there's a great deal of effort also to restore these prairies to maybe some of their original composition, and much of this is done by actually volunteers. So the take-home lessons from the Puget Lowlands are basically the same as from the Olympic Peninsula. Climate change will cause shifts in forest composition, and in this case, I think major shifts in the actual amount of forests on the landscape. Fire regimes are affected, and the human dependency on these resources are also affected. So now we can shift to sort of put this a little bit in the context of current climate change. And I think it's interesting when I think of current climate change, I again come to the name of a single person. In this case, it's Charles David Keeling, who died just last June but made a tremendous impact on our investigations of the Earth's atmospheric and ocean changes over recent years. He was funded in the late 1950s to take some measurements of carbon dioxide concentrations on Mauna Loa, and he did this for several years, and then his funding was cut off and had no support to continue these measurements, but he felt they were important, so he continued them on his own for a couple of decades until it became obvious that there was a long-term trend in these records to the upswing. And at the same time, there was observations of warming of the Earth's atmosphere and temperature records. And with knowledge of the greenhouse effects of carbon dioxide, then people became concerned about the potential for anthropogenic forcing of climate because the trace gases of carbon dioxide were increasing due to the burning of fossil fuel and other activities. So then research started to try to understand whether this trend in the 20th century was unusual over the long term. And some of the research went to Greenland, where the accumulation of ice captures bubbles of air, and the concentration of carbon dioxide could be determined in those bubbles. So you could extend the record of carbon dioxide back in time, and that indicates how strong this increase is in the 20th century. And then, in addition to that, there's been a great deal of research with dendrochronology, interpreting tree ring variations in terms of climate. And this is I think, generally accepted record of northern hemisphere temperature over the past approximately 1,000 years. The red on the right are instrumental records that come from thermometers and such. And the blue that continues to the past are reconstructions based on primarily tree ring records. So it's called a hockey stick graph because the upswing at the end, I guess, looks like a hockey stick. So that's, if you ever get bored, you can impress your neighbors that you know what the hockey stick is. Okay, there is this is sort of a recent collation of data, but for a long time people have known of the cold interval from about 1,400 years ago to the middle of the 1800s as the Little Ice Age. It's given that name because of the evidence of alpine glaciers being much more extensive in the preceding several centuries. This is the Emmons Glacier from Mount Rainier, and you can see the strong evidence of Little Ice Age conditions. The yellow is the indication of the moraine that surrounds the edge of the glacier, and it was at this location in the first part of the 1800s. So there's a lot of geologic evidence that the 20th century is warmer than previous centuries. And there's also quite a bit of biological evidence of a major change in climate about 100 years ago. This picture is taken from the Medicine Bow Mountains in Wyoming. And the main tree in the foreground is a single tree, but its growth form has changed dramatically over time. The tree is about 300 years old, and the trunk of the tree is quite round. But for a long time, this tree could not, the buds of the trees could not survive above the level of the winter snow. The winters here are exceptionally cold, and they're very windy, and the snow is easily blown by the wind. And so for the first 200 years of the life of this tree, it was not, the buds were not able to survive above the protection of the snow. But then conditions changed about 100 years ago, or a little more than 100 years ago, so that some of the buds were able to grow, and they actually successfully survived and took the upright form that you see on the left. Certainly the conditions are still very severe in this location because all of the branches on the windward side have died. So this very distinctive growth form is a really strong statement about the history of the climate. And as a graduate student of mine several years ago, Chris Earle, did his PhD in this area. So he has dates of the base of these bushy portions of the tree, and they're all 2 or 3, or some of them are 400 years old, but the upright portions are all dating from the late 1800s. So there certainly was a change in the climate in this area that's recorded in the appearance of these trees. Now in the Cascade Mountains, the trees are not as damaged by wind, but there are very high snow loads. And the change in the 20th century probably affected more the recruitment processes of these populations. And so in virtually all the high elevation meadows, especially in the moist parts of the Cascades, you can see a distinctive young cohort of trees that established in the 20th century. And the other trees that are older are typically growing on higher places where trees could be established during the Little Ice Age. But it's only in the 20th century can these very flat, wet meadows support the germination of seedlings, because now the duration of the snow is long enough that seedlings can become established. And then if we look at we'd take a core of these trees and measure the rings, in these high elevation locations you see a dramatic shift in ring widths starting sometime in about 1900. These records start in about 1600 AD and go to 1980. And so you can see, again, evidence of the 20th century warming. There's also questions about whether the climate change is affecting fire frequencies and insect regimes, and certainly there is a lot of evidence that that's the case, but this is much more difficult to determine in terms of the cause because of the human management impacts on these forests, which are also altering them and may result in fires and insect outbreaks. So the projection for the future climate in the Northwest is being made to a large extent by people working at the University of Washington. This is a projection over the next 100 years or so. And as you can see, there's a lot of variability in these projections, upper limit and lower limit of possibilities. And I'm just putting these numbers up mainly to show you that the projections for the temperature is for an increase of maybe 3 degrees by 2040, and the precipitation increase is about 2%. Well, a 3-degree temperature change is a large temperature change. It's almost equivalent to the differences between the early Holocene and what people think is the mean of the late Holocene. The projections are for wetter, warmer conditions, and the temperature increase is supposed to be felt in all months. So it's supposed to be warmer year-round by these projections. And I want to point that out because the early Holocene was a period that probably was much warmer and drier summers, but colder winters. So this is the caution that you must take when you try to carry evidence from the past into the future, because the conditions may not be exactly the same. But nevertheless, I think the lessons, the general lessons can be taken. And so the key challenges I see when we're trying to understand what the responses to future climate change will be involve a large number of things. Our understanding of the Earth's climate system as a whole and the climate system of the Pacific Northwest, the impact of the great landscape diversity that we have in a mountainous regions like the Northwest, and then the individual responses of the species. And we know that each one of them are unique in terms of their genetic makeup, their evolutionary history, and so we should expect them to be different, and one size doesn't fit all in terms of predicting forest change. Because we know something about Douglas fir does not mean that we can anticipate that its associates will behave in a similar way. And also, at this point, I'd like to remind you that the Holocene is a relatively warm period of time in the long-term evolutionary history of these species. And so we're also dealing with a species that may have been adapted to different, substantially different conditions than we will see in the future. So in summary, the insights from the past that I think are important are the general features of vegetation responses to a climate warming or any kind of climate change of the magnitude that's projected. And that's that forest composition will change. And it will change in a way that might be difficult to predict because each species will change independent of its associates. It's important to know what those individual characteristics are before we can make predictions about actually what will happen. We should expect disturbance and pathogen regimes to change, and certainly to the extent that we are dependent on our natural resources, I think the human economy will be certainly also seeing major change. And I will close just by emphasizing that the themes that I've emphasized from the Pacific Northwest are not unique to the Pacific Northwest. A talk like this could have been developed for Alaska, for the eastern United States, for Europe. These are common themes that are seen repeatedly in records wherever people have done research. So I thank you very much for listening. And